So now let's see some. I'll introduce you some with some new concept, which is called convolution. What is convolution? Okay. So suppose some input given image. Suppose one image is given to you. This kind of image. Okay. Where all the things, all these things are like all the pixels are in this form. So how much? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It is basically 6 by 6 image. Okay. Now we define a kernel. We define a kernel of size, say 3 by 3. It's a 3 by 3 kernel. What is this kernel? This kernel basically is put on the top of this image. Okay. How? I'll say that initially I have put this kernel here. 1, 2, 3. 1, 2, 3. 3 by 3. Is it fine? If I impose here, if I put this here, is it fine, guys? Can I put it here?
Yes.
Yeah. Okay. Now this kernel, what will it do? Okay. This kernel, what will it do? This kernel, or we can also say it as filter. Both the same things. What filter will do is, it is basically trying to get the features from the images. How? We'll see that. Suppose this kernel is say -1, 2, -1, 0, 0, 0, 1, -2, 1. Okay, any value. Now this kernel basically will go here, and whatever the pixel values here, say 68, 25, 205, 300, not 300, it will be 130, it will be 111, 110, 100, 195, 251, and 255. This is the pixel value. These are the pixel values from the selected portion. It will be superimposed here. Okay. Now, whatever the multiplication of these corresponding values, -1 times 68, 2 times 25, -1 times 205, all the values will be stored here in a new 3 by 3 kernel. Okay, got it? So not this small. The new image, say this one is my image. Okay, again 6 by 6. Say 6 by 6 image I have. So the output will be this one. Whatever the values coming from this multiplication of this kernel versus this selected portion from the image, 3 cross 3, it will give you some value which will be stored here. Again, this kernel, the same filter, will move one step ahead. The new thing will be selected from here till here. Okay, again it will be multiplied, summed up, and will be put here. Similarly, all the values of the pixels will be all the the selected image, this image will be convoluted with this kernel from all the different pixel values from all the locations. When we do such kind of operation, right, this is called convolution. This is nothing but your convolution. Okay, so suppose this image is given, this one is the image. Okay, after that what I am doing is, from this image I have got two different images. After applying two different kernels, I can apply n number of kernels. That's fine, that's up to you. This is the hyperparameter, how many kernels you want to select. Okay, and based on that, whatever the final outcome which we will get, this is the final outcome, right, after convoluting the images by this kernel or filter. This is called feature map. Okay, so here given some image, from one of the kernels I have applied the convolution operation based on one of the kernels, say K1, and another kernel, say K2. The first kernel is giving all the information about these things. Can you see here? Guys, can you see here? All the information about the horizontal edges. All the horizontal edges. Say here, let me change the color. Say here, these are nothing but the horizontal informations from the images. Can you see? All the horizontal level informations are extracted by doing this convolution operation by some kernels, some filters. Similarly, when I apply some kernel K2, another kernel, it will give you all the vertical level information, edges. Can you see here? All the informations. And if we combine all those, you will get the final picture, right? So similarly here, can you see here? Two kernels, say K1 and K2. I have two feature maps, and I have applied the convolution operations by two kernels K1 and K2. When I combine those two, I am getting this kind of pictures. These pictures are nothing but the features. These pictures are nothing but the features extracted from your image. Okay, which is basically performed by kernel. Okay, now look at this one. Suppose I am giving one input image, this input image, original image. I'm applying one kernel. I'm applying the second kernel. The output feature map from after applying the convolution operation by first kernel will give you this one. The output operation, the output feature map, which I am getting as a result of convolution operation by the second kernel, is this one. These two are called feature maps, which are nothing but the features extracted from the images. Okay, this will give you n number of different features, information about your vertical edges, information about the horizontal edges, information about the color combination, information about the intensity, information about the texture. All the information will be provided, will be extracted in a feature map, in multiple feature maps, which is extracted as a result of convolution operation by different kernels. Okay, now you will ask me that how it happens, right? How it happens. So basically, uh, while selecting the kernel, you can select any kernel of 3 by 3, 1 by 1, 2 by 2, 5 by 5, 11 by 11. Any kernel you can select. That's up to you. But these are nothing but the hyperparameters again. What is the size of kernel do you want to select? These are nothing but the hyperparameters. The less number of kernels if you select, the more and more complex the calculation will be. Correct? Each and every pixel you have to apply, that will be time consuming. Also, when you select the less kernel size, the shorter kernel size, there will be some problem. What will the problem? The problem will be like you will not get the neighboring information of the images. Suppose I am selecting this one kernel size here. I'm applying one by one, which will be this one only kernel size, right? I'm applying here. I'm not getting any neighbor information here, 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 or here, here. I will not get any neighbor information from the image. Okay, and that's the reason we should use such kind of kernel, such shape of kernel, which is very convenient for the images. Again, the way we move the kernels on the images, as I mentioned here, we'll again have to move the kernels from here to here, the next kernel. Sorry, the same kernel, the next, what do you say? We will just place the kernel on the next part of the images. Okay. So how many steps are we taking? We can also move directly here also, directly here. That is fine. We can also move here on this portion, 3 by 3. But that will skip these things, do parts. Okay. So the step we move, I mean, we have something called stride, which basically tells you about the number of steps the kernel, this kernel is moved during the convolution operation. And this feature map, what we are getting, feature map, the size of the feature map will be reduced. When we increase the stride, number of strides, then definitely the feature map will be reduced, right? That actually happens. Now, from this one, we have applied two different kernels on the same image and we are getting two feature maps. Okay. This is nothing but a part of your convolution neural network. That's what it happens in a convolution neural network. Okay. There are some, there is a very basic architecture of the convolution neural network. Okay. What is the architecture of the convolution neural network? So here we have some standard CNN architecture. What is the CNN architecture? Suppose I am providing some image. This is an image layer. This is the image. This image will be passed through some operation which is called convolution. Convolution. Now after this convolution, this will be passed through some non-linearity. Okay. After this non-linearity, this will pass through pooling layer, pooling operation. What is this pooling operation? I'm coming to that. Pooling. Okay, these are the triplets basically. These are the triplets. Again, you can have convolution, nonlinearity, pooling. Again, convolution, nonlinearity, and pooling. This will go on. And finally, what we'll be having is we'll be having fully connected layer. This is called fully connected layer or fully connected network FCN. And this one will basically, when we apply any function, it will be used for classification of images, where it will give you the classes. Class. What is happening here? Okay, class. This is the typical architecture of a CNN, where the triplet, this triplet, convolution, nonlinearity, and pooling. This triplet is repeated based on how depth is the network. Okay, the more and more triplets you will be adding, the more and more depth will be there in the network, and the more and more complexity will be there in the network. Okay, now if you are passing some grayscale image, so images will be having say size say 28 cross 28. Okay, this size will also take, so it basically, this image input layer will take basically image in the format of say input size. It will ask you input size. What is the input size or input shape of the image? You will have to provide. You provide 28 cross 28. It will ask you another parameter, which is called channel. What is the channel? Channel is whether it is a grayscale image or whether it is a colored image. In the grayscale image, the channel will be only one. In the colored image, the channel will be how much? 3 RGB. 3 channels. Correct. Correct. Now, the filter or the kernels basically, that will be convolved with any RGB or grayscale image. Okay, that can also be either 3D, 3 cross 1, or 2 cross 2 also, 1 cross 1 only. That's fine. It depends what kernel size, what kernel shape you are choosing. That is basically hyperparameter. Okay, and for multiple kernels, when someone asked multiple kernels, right? I have say multiple kernels, stacked kernels. We can have multiple kernels, right? And for multiple kernels, after convolution, all the feature maps obtained from distinct kernels, from kernel 1, kernel 2, kernel 3, kernel n, all the distinct kernels are again stacked together like this one. All the feature maps will be stacked together only like this one. These are the feature maps after convolution operation by kernels. They will be stacked together. Okay, and after stacking it, we can apply something called pooling layer. Pooling. What is this pooling? Okay, pooling means you just have to get, I mean, to pooling. This pooling will basically replace the output of any node at certain location with some summary statistics of with nearby locations. How? We'll see that. Suppose in the feature map you have got this kind of one of the feature maps. You have this one. Suppose this one is the feature map. Okay, this feature map say is having 4 by 4 matrix. It is possible, right? Feature map based on the kernels, you have got the feature map. Suppose this is 4 by 4. Suppose this one is having 3, suppose 2, 5, 6. If I write 3, 8, say 1, 2, 1, 1, 4, 4, 6, anything it will be like, okay, 9, 8. If you are applying the pooling operation, I can apply pooling operation in multiple ways. One is say max pooling, one is say average pooling, one is maybe minimum pooling. Anything can be have. Anything. That's up to you. That is again the hyperparameter. Suppose I am applying max pooling, max pool operation with how many? Say 2 by 2 window. Okay, with say a stride equals to 2. How will I get? Tell me. Max pool operation with window 2 by 2. 2 by 2 means this will be first selected. First 2 by 2 will be selected. 2 by 2. Okay. When 2 by 2 is selected, now tell me what will be their max pool operation. The maximum value of the pixels will be here. Maximum value. What is the maximum value? Here, 9.
9.
Again, if I have selected a stride equals to 2, it will move 2, means 1 and 2. Again, this one will be selected. What is the maximum value? 6. Again, in the next one, what is the maximum value? 4. Again, it will move 2 strides away. How much? 8. This is the output of your max pool layer.
Yes.
This is nothing but your pooling operation. Whether max pooling, mean pooling, whatever you can do. That depends on you. And we discussed something about, say, convolution. As a part of convolution, after that we will do non-linearity. What is that non-linearity layer? What will happen here? We can apply any function, any non-linear function. So majorly, ReLU is the mostly used non-linear function in CNN. However, we can also use another one also, another non-linear function. That's up to you. Okay. Why do we use this one, the ReLU? There is some reason for that. Inside the within the hidden layers, why do we use the ReLU function, ReLU nonlinear function for the nonlinear operations? There is some reason. This ReLU operation, this ReLU function is nothing but an element wise operation. Okay, applied to each and every pixel, and it will replace all the negative pixel values in the feature map by 0. Right? What was the ReLU one? Do you remember, guys? What was the ReLU doing there? Right? So it will replace all the negative pixel values to 0 with 0. Now you will ask me that why we will get the negative pixel values. In what cases we can get the negative pixel values? Suppose there are some error or noise in the data. Noise, basically. When you are having noise in the data, you can get the negative pixel values. Okay. Or suppose in a image, it is the pre-processed image basically. For example, you are getting some pre-processed image. Some object detection would have happened previously. Okay. So some boundary is defined. Inside the boundary, some pixel value will be there. Outside the boundary, the negative pixel will be there. In such cases also you can get the negative pixels, and those negative pixels are actually not defined because the pixel values will vary from 0 to 225 only. Okay, now when it varies from 0 to 225, then it will be a problem. What problem? You will get negative pixel values. In such cases, we have to do the nonlinearity, and during the nonlinearity, your sigmoid function will not be able to handle those negative values of the pixels. And that's why we should use the ReLU activation function in the hidden layers.